We're going to model a wind turbine. So our next model is going to be of an energy extraction device, that is a turbine, something that takes energy out of the fluid flow. First model we did, of course, was of a pump, which put energy into the fluid flow. So in this case, we'll look at wind turbines. Wind turbines, of course, very important to our region. We have one of the largest wind resources for energy in the entire world off the coast of Massachusetts and Rhode Island. There's a lot of interest in trying to harvest some of that wind energy and turn it into electricity. And wind turbines, of course, are the way that you do that. So there are a lot of people working on that in this area, including faculty at our own university, like Banafsheh Syed Hagazadeh, who is going to come visit our class, or maybe already has visited by the time you watch this. So anyway, the idealized wind turbine model, here's what it looks like. You have a velocity coming in from the left here, and it's coming at some velocity v1, and pressure, atmospheric pressure here, P naught, and it goes towards the turbine, and then it goes through the turbine, and it will go through the turbine at a slightly different velocity perhaps, and then there will be a wake region behind the turbine, could be broader than the region of flow that actually interacts with the turbine as the wake expands past the turbine. And that wake has a velocity v2, but of course the pressure has returned back to atmospheric pressure as soon as it basically gets past the turbine at all. So if you were to map the pressure here underneath this, the pressure is P naught, as the wind approaches the turbine. As it gets near the blades, the pressure will increase, causing a pressure difference on the turbine blades, which of course will drive the turbine blades. And the backside of the turbine blades will have lower pressure, again, contributing to that driving force that will cause the turbine blades to spin. But then as the wind passes, the air passes past and goes out to the atmosphere, of course, it returns to its simple atmospheric pressure. So that's the pressure distribution we expect to see. Higher pressure on the front side of the turbine blades, lower pressure on the back side. But basically everything else is at atmospheric pressure. And certainly if you look at this control volume, all the surfaces here that I've drawn are going to be at atmospheric pressure. So there's going to be no net pressure effect on this control volume. That's going to matter to us later. All the pressures on the outside surface of the control volume are P naught, atmospheric. And there's no fluid crossing the control volume boundaries except at the inlet and at the outlet. So this has been drawn to try to capture the fact that fluid will be deflected around the turbine, but that fluid will not leave our control volume as drawn. Here are the three velocities: V1, the wind speed approaching the turbine; V2, the wind speed in the wake of the turbine; and then V, which is the wind speed as the fluid actually passes through the turbine blade region. All right, so looking at our control volume analysis, we can start to calculate some information about forces. So we're just going to be focused now on the control volume that I drew. So it looked a bit like this. And it has the turbine in it, but the turbine is in the center, far away from any of the entrances or exits. Here's our V1 volume, our V1 velocity as fluid enters. Here's our V2 velocity as fluid leaves that region. And that's our control volume. So now we're going to have the Fx equation that remember from integral analysis. So we're doing an integral momentum analysis here. So we have the time rate of change of the control volume of its momentum. So that would be the density times the velocity time derivative. And then we have to add the fact that the velocity of the fluid, or the momentum of the fluid entering and leaving the region, will probably be different. So we need to take care of that with this surface integral. So here are our two integrals we have to take in order to assess how much force must be applied to this control volume. Well, this is 0 because we're saying, again, steady state, and so the control volume is not changing its momentum. Things are just staying the same in this control volume over a time, so there's no time dependence. The wind is blowing steadily. We're assuming nothing is changing in time. But this is non-zero. We have fluid definitely entering and leaving. So we'll go ahead and analyze those terms. So this is 0 because of steady state, but this other term is non-zero. So we only have the inlet here 1 and the outlet here 2, so we only have two surfaces where fluid is going to cross the surface. Notice this is only going to be non-zero where the velocity has a component that crosses the surface. That's the outward surface normal. That's dotted with the velocity, so there will be no contribution from the sides. So we only have to worry about the contributions from surface 1 and surface 2. Surface 1, we know that velocity is v1 there. We have the density, and then of course it's going to be minus v1 for this product v dot n, because the outward facing normal is of course going to face that way, and the inward velocity is facing the other way, so that's going to lead to that minus sign, and then we have to do that all over surface a1. And then we have the same thing for 2, except of course the velocity is now 2, and this is going to give me a positive v2 here, not a negative, because in this direction the outward facing normal and the velocity are pointed in the same direction. So those are our two integrals. Notice that v1 and v2 are constant. v1, v2, and v1 are constant. So we don't have to actually keep them in the integrals if we don't want to. I'm going to keep part of them in the integral. You'll see why in a minute, but I am going to pull part of them out. I'm going to pull one of them out. So I can pull them both out if I wanted to, but that doesn't actually achieve what I want. So I'm going to pull that v1 out because I can, because it's just constant. So it's in the integral, it's just a constant. And then I have rho v1 dA1, so I'm integrating across that surface 1. And the same thing over here, v2, integrate over surface 2, rho v2 dA2. And the reason I left that other velocity in there is because this grouping and this grouping, rho times the velocity integrated over the area, rho times velocity integral, those are the mass flow rates. So I'm going to go ahead and say I have Fx is equal to minus v1 times the mass flow rate into that control volume plus v2 times the mass flow rate out of that control volume. So these guys are just m dots. So I'll call that m dot 1, m dot 2. But of course, m dot in equals m dot out, because mass in has to equal mass out from our control volume at steady state. So we have an expression for the force, which is just the mass flow rate, whatever that flow rate is, v2 minus v1. So that force says that the, that's the force that must be exerted in order to keep that control volume somehow immobile. And so the net pressure force is 0, as we said. So that force could include pressure forces, but the net pressure forces equals 0 because there's atmospheric pressure all around the control volume. So there's no net force resulting from all those pressure contributions. Net pressure force equals 0 because P equals P0 at every point on the control surface boundary. So there's no net pressure effect. So the net force on the turbine then is equal to m dot v1 minus v2. So at v2 minus v1, that's the force that has to be exerted to keep things from moving. So that means that the force being provided essentially by the post of the turbine has to be this, but that means that the force being exerted on that fluid, the net force on the turbine, is this force. So we have a higher velocity coming in, a slower velocity leaving. That's going to lead to a positive force on the turbine. The turbine's going to, if you want to keep the system immobile, you're going to need to anchor it to the ground and exert this much force in the other direction, this negative x force, to keep it from moving. So that's the first result we have for this turbine analysis, is how much force we need to apply in order to keep those blades, that whole turbine, from just blowing away.